All right, today we're going to tackle a really fascinating challenge. How do we teach computers to understand our world in 3D? Now, this sounds straightforward, but believe me, it is way, way harder than you'd think. So think about it. We live and breathe in 3 dimensions, right? But for the longest time, our smartest AIs have basically been stuck in flatland, only able to see 2D images. And there's a really good reason for that. Adding that third dimension, well, it just unleashes a crazy amount of complexity. You see, the problem is when you add that z-axis, the computational cost doesn't just go up a little bit, it multiplies. It grows exponentially. This is a famous problem that researchers call the curse of dimensionality. Okay, to really get this, let's break down how a computer sees. A 2D photo, that's just a flat grid of pixels. Pretty simple. But a 3D object, that's represented by a cubic grid of what we call voxels. You can literally think of them as 3D pixels. So we're not just going from a square to a bigger square, we're going from a square to a cube. And for a computer, that is a monumental leap. And here is the real kicker. The cost, both in terms of computation and memory, grows cubically. What does that mean? It means if you double the resolution of your 3D model, you don't just double the cost. No, you increase it by 8 times. This is why for years, most 3D AI models were stuck with these super low-res, blocky shapes that just couldn't capture any real detail. And this chart, which is based on the original OctNet paper, shows you exactly why this is such a showstopper. For standard, what they call a dense network, the memory usage just goes through the roof. A 64-cubed resolution model, okay, that's about 12 gigs of memory. Push it to 128 cubed, and you're at 96 gigs. And 256 cubed, you're talking about a staggering 768 gigabytes of memory. Your typical high-end GPU, yeah, no way. It can't even touch that. So this seemed like a totally impossible wall to climb. But then, some researchers had this critical insight, a real wait a second moment. They asked, what if we're wasting all this massive computational power on, well, on nothing? Think about pretty much any object around you, a chair, a car, even the room you're in right now. They're mostly hollow, right? They're defined by their surfaces. But a dense voxel grid, it treats all the empty space inside an object and all the empty space outside of it with the exact same importance as the surface itself. And that is just incredibly, wildly inefficient. And that very simple question leads to a truly elegant solution. It's one of those ideas that was kind of hiding in plain sight, borrowed from the world of computer graphics. The answer, it turns out, lies in a really clever data structure that's actually been around for decades. But now it's totally revolutionizing AI. It's called an octree. So what is an octree? Well, fundamentally, it's a way to represent 3D space adaptively. So instead of a rigid, dense grid that treats every single point the same, it's a smart, hierarchical structure. It only puts detail and computational power where it's actually needed. Let me walk you through how it works. You start with one giant cube that covers your entire object. Then you ask, is there anything in here? If the answer is yes, you split that cube into 8 smaller cubes. That's where the name Octree comes from. You just keep repeating that process, splitting the cubes that have data in them into smaller and smaller pieces. But, and this is the crucial part, if a cube is totally empty, you just stop. You don't split it again. That one single node now represents a huge chunk of empty space, which saves an absolutely massive amount of memory and processing. And this is the core idea behind OctNet, right from the original paper in 2017. By building a neural network on this super efficient octree structure, the AI can focus its memory and its computation only on the important stuff, the relevant dense regions. So, okay, that's the theory. But what does this actually get us in the real world? Well, being able to use high resolutions isn't just some technical victory lap. It unlocks completely new abilities for AI. But what's really interesting, as the research showed, is that you don't always need to just crank up the resolution for every single task. It's a bit more nuanced than that. So, have a look at this. For a pretty simple task like 3D object classification, which is basically just answering the question, what is this thing? As you ramp up the resolution from a blocky 32 cubed to a super detailed 256 cubed, the accuracy barely even moves. It seems like after a certain point, more detail just doesn't really help an AI tell a chair from a table. But now, look at what happens when you give the AI a more subtle task, estimating the orientation of that object. Figuring out which way that chair is actually facing. Here, the results are completely different. As the resolution goes up, the error rate drops consistently and significantly. The AI gets much, much better at understanding the object's specific pose. At a really low resolution, the AI is pretty much just taking a wild guess. The object is just a fuzzy blob. It can't see the fine details it needs, like which way the legs are pointing or where the back of the chair is. So its predictions are just scattered all over the place. But at high resolution, bam, the payoff is crystal clear. The predictions become sharp, confident, and they're all tightly clustered right around the correct answer. The AI can finally see the subtle geometric cues it needs to really understand the object's position in 3D space. And this benefit, it extends to even more complex, really important tasks like semantic segmentation. This is absolutely critical for things like self-driving cars or advanced robotics. This is where an AI doesn't just need to know, hey, there's a car over there, but it needs to label every single point in the entire scene as car, road, person, or building so it can navigate safely. So at the end of the day, the breakthrough of Octanet wasn't just about making things run faster or use less memory. It was about making AI fundamentally smarter by teaching it how to be more efficient. So let's just recap the whole breakthrough here. The problem? Dense 3D grids were just too expensive to compute. The insight? Realizing that most 3D data is actually sparse. It's mostly empty space. The solution? Use a clever data structure, the Octree, to focus computation only on the parts that matter. And the payoff is huge. An AI that can finally process the rich, detailed geometry of our world at a resolution that actually means something. This shift in thinking, from dense to sparse, was a fundamental leap forward. It's a key step towards a future where AI can perceive and interact with our physical world just as naturally as we do. And that leaves us with one final, pretty mind-bending question to think about. If an AI can truly see and understand the 3D world with the same level of detail we can, what comes next? What will it be able to build, to navigate, and to create?